So this is a retrosynthetic problem. So again, these are the ones where you're given the starting materials and you got to look starting materials on the products and you got to figure out a route to make this. So the first thing, easiest thing to do always is to go ahead and number your carbons. 1, 2, 3, 4. And then try to number those on the starting materials. This will be 3 and this will be 4. And the reason I know that is because if there's the oxygen, right, this is telling me, right, this is an aldehyde, right? So I'd write to myself aldehyde, and I only know one way to make an aldehyde, and that's with BH3, right? So I know I have to have an aldehyde, so I need to use BH3. That's that anti-Markovnikov thing. I'm also adding 2 C's, so that makes me realize I'm going to need NaNH2, right, the minus, the plus. What else? Looks like I start with 2 bromines, and I need to make an alkyne, so I'm going to need to do that double elimination. All right, so remembering how to do that. So there's some notes for myself I can just look at. And again, I know this is 3 and this is 4 because, right, wherever the group ends up, I know from an aldehyde, this came from, right, one step back from this, right, aldehydes all come from enols. All right, so 1, 2, 3, 4. The enol came from an alkyne, goes between 3 and 4. 1, 2, 3, 4. This came from a different alkyne, right, that had carbon 3 and 4. And that came from that. Now going forward, to think about this, to get the 2 pi bonds, we need to do excess Na plus NH2 minus. All right, I do double elimination. For this step, I need to do step 1, NH2 minus again. And step 2, I need to add 2 carbons. So I need to do something like this, the bromine. And this would be carbon 2, and that would be carbon 1. Do the SN2. And then on this step, I'm going to need step 1, BH3, and then step 2, H2O2, and OH minus. And then here is just taut, so that just goes to that. So again, right, lots going on. Started 2 carbons, and with 4, got to add 2 carbons. Aldehyde must have a BH3, had to have an enol, anti-Markovnikov addition. Right, double elimination. That's going to be excess strong base to do the E2 twice. All right, so ozonolysis type problem. So what you have here is 2 carboxylic acids. So first of identifying 2 carboxylic acids, I'll give another example here. And for this one, we'll only have, let's see, all right, 2 aldehydes, we'll say, or an aldehyde and a ketone. And we'll see what the products are for both of them. So if you work back where it's here, you can see essentially where these pieces need to come together. That's the idea. So numbering, again, these carbons. So 1, 2, 3, and 4. It's going to go 1, 2, 3, 1, or 4, 5, 6. I didn't number the other ones, but it's okay. If you see 2 carboxylic acids, you should recognize that this is going to be an alkyne starting material. If you see a ketone and aldehydes, you need to recognize that this is going to be an alkene starting material. So we also need to recognize for both these, the carbons of the carbonyls are the pieces that come together. So they're like this is going to be a pi bond. And if this is 1 and that's 3. It needs to identify what else is bonded to 1. And actually, sorry, it's going to be an alkyne. So 1 was bonded to 2, which is here. And then 4 is bonded to these 4 methyls. So just recognizing the carbons of the carboxylic acids when the pieces coming together. If they're ketones and aldehydes, then it's an alkene, not an alkyne. So again, same idea. Draw the alkene out. Carbon 2, carbon 4. It doesn't really matter the cis or trans, however you want to do it. Usually draw it as trans just because that's the more likely one. So 1, 5, and 6. And of course, I forgot 3. That's why we number atoms. There's 3. And that's where the 2 pieces come together for these ozonolysis. But again, numbering is really important to not lose stuff. And then again, just to clarify, how do I know if it's an alkyne or an alkene? So I know it's an alkyne when I see 2 carboxylic acids or carbon dioxide, CO2.
Does it matter how you number your carbons again?
Doesn't matter. The numbering has nothing to do with anything as long as you number them and don't lose them over here. But if you see carboxylic acids or CO2, right? CO2. This is telling you it's a terminal alkyne. 2 carboxylic.
You're muted.
Right, so if you had CO2 as a terminal alkyne, if you have 2 carboxylic acids, it's an internal alkyne. Aldehyde, or ketone and an aldehyde, again, tells you it's an alkene. So those are things you can kind of start to recognize, and you'll see those things. Numbering, you can number however you want to, just don't lose atoms. But recognize if you have a CO2, that you don't have an internal alkyne, you have a terminal alkyne. That's the other big thing to recognize. All right, ozonolysis again, taking a look, given the start material and the reagents, and then what's the product. So again, a good numbering system is the key here, and you're just cutting that in half. So I don't need to make it look pretty by any means. Just putting a carbonyl there. So there's carbon 1, and there's carbon 2. Nothing else changes. For this one, if I call this carbon 1, and this 2, 3, 4, 5. This one you're putting them back together, so 1 needs a bond to 2. And because they're aldehydes, it's an alkene starting material. So we can call this 1, 2. And let's see, 1 is bonded to 3. 2 is bonded to 4 and 5. 3, 4, 5. So it's kind of putting it back together there.